Breaking news, global warming is causing irreparable damage to the Earth. What can be done?
Introducing the Jet Set, a team of 5 dedicated aspiring engineers who will protect the Earth, and the Olympus Nimbus, an aircraft designed to disperse aerosols into the stratosphere to temporarily reflect solar radiation and mitigate rising temperatures.
Awesome, and here is the Olympus Nimbus. That's our final design. This is Team A306, the Jet Set. This is for Aerospace 251 Intro to Aerospace Design. I'm Ian.
I'm Elizabeth.
I'm Jamie.
I'm Joyce.
And I'm Samuel.
Awesome, and let's get straight into it. So the first thing we had to do is identify our stakeholders and their requirements. So this is a great example of our stakeholders right here. So some stakeholders of ours are the government, investors, engineers, the FAA for certification, and so on. And from these stakeholders, we were able to find requirements. For example, our main mission required cruising 200 nautical miles out and back for the dispersal of the payload. You have to do this at an altitude of 65,000 feet with a payload of 35,000 or greater, with a cruise speed of Mach 0.5 or higher and a crew capacity of 4.
You're probably wondering what the risks for our aircrafts are. First risk here is the aircraft running out of fuel. This is a low probability, but it would have a decently high severity, as if the aircraft runs out of fuel, we'd have to glide to the landing spots. Icing conditions is not high severity, as we have TKS icing systems to deal with that. For engine failure, it's not a big problem, as we have 4 engines, so if one of them turns off, we lose a little bit of maneuverability. But for the last one is damage to the aircraft, which is a high severity, as if things were to happen to the aircraft, it would have a lasting effect on the crew members.
Concerning our design process, our concept generation was inspired and came from the Boeing B-52, the Lockheed Martin C-5 Galaxy, the Martin WB-57, and the Avro Wilcon. And our design process comes with some special design features like the unswept wing platforms for the stability and lift for the aircraft, a multi-bogey landing gear, and 4 Rolls-Royce AE3007 turbofan jet engines.
Awesome, and so we conducted some calculations, some initial calculations are shown here. The first thing we had to find was wing loading, and we had to choose between a low or high wing loading depending on our requirements. Our requirements favor low wing loading because we have high atmospheric cruising, which is more favorable with higher lift. And so from here, we were able to estimate the maximum takeoff weight and then find the surface area of the wing. From here, we were able to estimate the aspect ratio using past literature and then find the wingspan. After that, we were able to find the mean chord, and then finally, we were able to estimate the surface area for the vertical tail and horizontal tail by finding the length from the center of gravity to the quarter chord. And so here are some of the parameters calculated here. So wing loading is 50 pounds per foot, which is in line with the U-2 and the B-57 Canberra, which are some comparable planes. It's just a little bit higher for the added payload. And then the aspect ratio is 8.5, and those are our surface areas, and we have a mean chord of 12 and a wingspan of 105 feet.
Then we decided upon our airfoil, which was the NACA 64A410. The maximum chord thickness of this airfoil was 0.1. It's a circular arc leading edge shape, and we ended up not having a wing sweep as it was not advantageous since our aircraft did not cruise as fast. And here's our wonderful Olympus Nimbus. As you can see, you have a better representation of the wing shape, the tail shape, and you can see our 4 engines mounted under the wing.
So now that we have our design, we're trying to prove to you that it works. We first did this by plotting its thrust required and available as a function of altitude. This intersection here of the 2 curves represents the flight ceiling, or the maximum altitude that the plane can fly at. It occurs at around 100,000 feet, and this is much higher than our required cruising altitude of 6,500 feet, proving that our plane is capable of flying this high at cruise. So it can fly that high, but how fast can it fly? We plotted thrust required available again, but this time as a function of velocity at 65,000 feet. The intersections here represent the minimum and maximum velocities possible based on our 4 engines. The intersection here is the minimum velocity is around 500 feet, which is lower than our required cruising velocity of around 600 to 700 feet per second. This Yeah.
You're probably wondering what lessons we learned during this project. Some lessons we learned were communication and flexibility, as we had to work around each other's schedules. Now, the hard skills we had to learn were the MATLAB coding skills. We had to go derive the equations, but all in all, the most important thing for this project is the friends we made along the way. Thank you for tuning in this week. We are the Jet Set.